So we're trying to balance this kind of object, but not on a support that is put under it in when it is located vertically, maybe in this manner, okay? But rather we want to put it under it as if it is when it is horizontal entirely. So it's a flat object, and we want to balance it in this manner, okay? So which means that having one support is not enough. We know the x is for rather we're looking for two lines that would create give us where the point is located, one single point. And we already have one, okay, so that's the analysis that we did previously, and that's how we can balance it if it stands on top. But then that gives us at best, as if it's horizontal, this gives us at best this, okay? So we need another one that we are able to balance in this manner, okay? So along the or rather across the y-axis. Okay, so this is the analysis we started doing yesterday. So the region is balanced. Now this time it is with respect to the a horizontal line. So y equal d is that horizontal line, and so it is balanced relative to this horizontal line y equal d when the same exact balance equation is satisfied. So same balance equation in what sense? It is the total moment, okay? Total moment, which is the mass times the lever. But the lever now is measured, as I indicated over there. That's the piece of our region that I want to balance, the red one, and what I have there in purple is my lever, presumably. That's the question becomes what is the lever? Yes. What is the lever? The question that we need to figure out. What is the lever of each bar? Okay. So when it was relative to a horizontal line, it was very clear. So when vertical line. When the line was vertical, the answer was simple. So if this was x equals c, the answer to this question is this is the lever. Okay, so that's the horizontal lever. Now we're looking at a different situation. We're looking at y equal d over here. So then the lever is supposed to go somehow in a vertical manner, like this. Okay. So let's figure out what it is. I'm not sure. Maybe it will be clear once we have our function available, because we're going to be doing it one bar at a time. So you can think of it as a plank with a certain length, and we know what that length is. Well, actually we do. So this is the top, the bottom of this thing is 0, and the top is f of x. Okay, so that is the plank that we're trying to balance. Not trying to balance, rather we're trying to figure out where its what its lever is. Okay, so a plank, so a rectangle located horizontally, and what is its lever relative to y equal d? Let's think about that, what that lever is. So this is my rectangle. It goes all the way from 0 to f of x. Okay. So we're not concerned with the mass. Mass is taken care of right here. So we are interested entirely in terms of lever. So we're interested in lever entirely. So this is the question that we're trying to ask. So what is the lever? Well, the difference from the previous example is that it has a length. So the weight is distributed along this bar. Okay, so how do you figure out the lever then? So if the weight is located at a single point, like big heavy weight, then you know what the lever is. You just do the distance to that axis. But what if it's distributed like this? What should I be looking for? I should be looking for at a special point. I should be looking for at a special point on my bar. What should it be?
Shouldn't you be looking for the center of mass on the bar?
The center of mass of the bar, that's right. So that's pretty much the idea that goes everywhere in any kind of study of motion, is that you replace an object with its center of mass. And then if you know where it is, and in this particular case it's very simple because it's a bar, so we know where the center of mass is. It's halfway, right? So in fact, so this will be simply f of x over 2, right? From 0 to f of x, center of mass will be halfway because it's uniform. Okay, so the same thing you do when if you throw an object. If you want to know how it's going to trace the shape, you don't really have to look at the whole thing. You find its center of mass and just trace where the center of mass is. You think as if that's what Newton did himself. Look at where the force is. You think as if the force is applied to the center of mass of that object, and you see the initial velocity is also applied to that point, and that's all you need to do. The rotation, in addition, that is a separate issue. You don't have to necessarily worry about it if that's not your concern. Planetary motion, once again, replacing the sun with its center of mass, as if its whole weight is concentrated at center of mass. Same with the Earth and the Moon. Okay, so it's like 3 points moving in space, and that allows you to do all computation. Newton did it, all the computation as far as solar system is concerned. Okay, so and this one is simple. It's not round, so it was easy for round objects such as planets to find the center of mass is at the center because of the symmetry. This one has a different kind of symmetry, but it's still in the center. So then the height will be function over 2. Okay, so moving on to the actual data. So this is what we're trying to do. We still have our half circle, okay, and we're trying to balance it this way. So these two lines you can see over here, 2 rows over here. What we addressed, and I'll put them in the separated from the rest. Oops, no, like this. Okay, so these 2 lines, two rows, this is what we did previously, and we found the center of mass. We found the x coordinate of the center of mass, which is 0. Where's my 0? Well, we through trial and error, we ended up with 0 over here. Okay, so as you see, total center of mass becomes 0. So we're doing exactly the same thing, but now the lever now will be with respect to y equal d, a horizontal line. Okay, so but this will be the same. Coordinates are the same. Heights are the same. Weights are the same. Okay, the levers will be different. The moments will be different. So let's do the levers. Okay, levers, which we just discovered what it is. Okay. So if my location is -1, the height is 0. Well, that doesn't matter. Let's just look at one of these. So suppose I'm looking at one of these bars. Okay. So the mass already available, or weight is here in this row. I'm supposed to put here the lever, and the lever, as we just discovered, is the height, half of the height. Half of the height is my leverage bar. Okay, so I'll take it here, and I put it equal to my height over 2. Okay, height over 2. These are my levers for with respect to. Hold on a second. I forgot to subtract. So this is my lever with respect to the origin, but this is lever with respect to y equal d. So lever, so it will be, I have to subtract d, that's all. Minus d. Okay? No, d. That was stupid. minus wherever my D is located. This is my D over here, see? So it will be R2C5. Okay? So the lever of 0 at the leftmost point, the lever is, why is it? Yeah, the lever, the height is 0, and you subtract, and you have subtract 0.5, you have negative 0.5. So the negative lever at that location. The mass is 0, so that doesn't contribute anything. So anyway, so these will be my levers. Okay, let's take a look at them slightly. So let's just go left to right. I think these numbers are just positive, and that's why they don't fit. Okay, well. Okay, so it seems that they all tend to be negative. I wonder why. They're all negative. Let's think about why. No, that's not right, I don't think. So the height over 2, no, that makes perfect sense. Because I just chose a number that was not plausible. I chose the D to be 0.5, okay, so which means that it's exactly halfway between the height and the maximum height is 1, okay, so in the middle. So when I divide by 2, the maximum half height is 1/2, and that's why we can have either 0 or less. So let's put a number that is less than that. How about 0.3? Which is actually kind of plausible, right? So what I'm talking about is what is the proportion of where should I put that axis on this line where it's going to be, and what my conjecture initially is that it's going to be at 0.3. So here somewhere, you can see almost the dot here. So that's say 0.3. That might be my location of the center of mass. Okay. So and then I subtract 0.3 from my half heights. Okay, so as you can see then in the middle, you can see in the leftmost and the rightmost, the levers are negative. Why? Look at it this way. The lever. So, okay, this way. So the levers will be relative to this axis. They will be, they lie halfway, the half distances, half heights are below 0.3, and in the middle here they are above 0.3. That's why in the middle we have positive levers. So that is the tipping idea then. So these will be bringing will pull the object this way, and these will pull in the opposite direction. Okay, so that creates should create a balance. Right now there is no balance because well, maybe not. I haven't computed it yet. Now the next step is the weights and well, actually we have the weights already, so we just do the moments. Once again, relative to this line y equal d, and d is 0.3. Okay, so what do? We just multiply each lever by the weight. Okay, so it is equal to a lever times the weight, which is right here. Okay, lever times the weight. So 0, why? Because the weight is 0. Okay, so as you can see once again on the left, the weights are so small and the levers are small, so they don't really contribute a lot, turns out. Okay, in the middle the moments are positive. So together it appears to be a positive moment, which we can easily confirm if I take it here and copy it here. So yeah, 0.2. So take a look at what I'm doing here. The total moment is simply the sum of all of these entries, and it gives me the total moment of 0.2. Okay, so in other words, it's disbalanced, and it will be tipping that way. Okay, so if I put it support like this, it will be tipping that way. That's what positive means. If it was negative, it would be tipping that way. So, so then what do? Then I have 0.3. Then it's too far to my left and too far to the right. So I have to move it that way. Okay. So so instead of 0.2, what should I take? Instead of 0.3, I should make it larger. What do you suggest? Well, 0.5 is too far. We know that it's not going to be balancing at 0.4 because it's in the middle. You can certainly verify that. If I put 0.5 here, as you can see, moment is negative, it tips the other way. Okay, so that wider part it's just too heavy in comparison. If I cut right in half, then this certainly part is smaller than that part. Okay, so that's not going to work. Let's try 0.4. Okay, so it's better. It's better. 0.4 is better. It does balance on the total moment is 0.4. If I want slightly smaller, so what should I change 0.4 to what? 0.35. Hold on. What? No, I think we went in the wrong direction. Yeah, we went in the wrong direction. As you can see, the moment has increased, right? The moment has increased because we moved our axis towards the lighter part, which made the lighter part smaller and which made it tipped even more in that direction. So we have to go from 0.4. We should go to, say, how about 0.42, possibly. This is as close to 0 as it gets. Okay, so that's the moment 0.42, which means that indeed, if you take, I'm supposed to think, this is 1, okay, so this is 1, and I'm supposed to find 4.2 here somewhere. If I have I don't know, I should have here maybe a ruler, okay. Okay, so, so I have here 85 centimeters. So in order to get 85 centimeters, so 85 times 0.42 gives me 35.7 centimeters. Millimeters, I'm sorry, millimeters. Okay, so 4.4, what is that number? 35. Okay, it's 35, roughly, maybe 36. Okay, so I mark from left to right, 36. Okay, as you can see, it's slightly closer to this edge than to that edge because this one is thinner. Okay, and then I just draw a line, more or less, that suggests where my balance should lie. Okay, so as you can see, in addition to the horizontal axis that we already had before, I'm adding, that was vertical. So I'm adding a vertical one, and now I have the intersection, and that intersection is supposed to be a balancing point. Okay, so that is literally how the problem is solved, finding where the balance point of a half circle is. Well, I can just test it and see if it works at all. Well, it's reasonable, right? So, well, as close as it gets, but you can have this accuracy as high as you like, and it purely based on data and nothing more. You just if you need more accuracy, you just create a bigger spreadsheet. You can have a 10 times bigger spreadsheet, and then you'll have maybe 10 times bigger or better accuracy, and then the balance will be more accurate. And then now the next step is what if I want absolute accuracy? Okay, so absolute accuracy means that there is a, what does it mean? It means that, well, there's no approximation. So there's no approximation, which means that all of these summations will have to be turned into integrals. Okay, and then the integrals have to be evaluated in order to find in order to find the answer. So let me write it out. So this is, I think, is satisfactory. We found the center of mass by trial and error, changing the d-axis. Okay, that's fine. Now let's move on and let's try to find the absolute accuracy solution for the same thing. So then we have to figure out how this balance equation will be turned into integral, just the way we did it before. And that's really not too bad, because the mass is we are retracing our steps. So we know that the yi is in fact is equal to f of x over 2. In the meantime, f of mi is the mass, which is like, forget about the lever, which is that number, but now mass is the height times the width. So it will be f of x delta x. Okay? Like this. Okay, so what I'm looking at right now is my my moment. So that bar on the left that I have here, it is expressed in terms of the mass, just the way we did it. The mass, or weight, which is the height times the width. Okay, uniform density, so we don't care about actual density, so just the area is sufficient. And then I multiply by the lever, which is half of the height minus d. Okay, so that is my sum. Okay, and then it's supposed to be equal to 0. Okay, at this point, what do I do? Improve my partitions, making delta x go to 0. As delta x goes to 0, my sums turn into integrals, and this is my integral. So integral will be from a to b fx over 2 minus d dx equal to 0. Okay, so that is my equation. The balance equation turns into this, right? So you can set, once again, this is balance equation. You can compare it to the balance equation that we had originally. So that, once again, balance equation. Okay, but this one is the vertical issue. The balance equation that we had for the horizontal is very much similar. So, well, not very similar. In fact, it's somewhat different. It is the moment is different. So the moment, the one written in the given in the green box. Okay, so the function itself appears only as itself, and here it appears twice. So that x over there is replaced with f of x over 2. Okay, so that's my balance equation. I solve it. Same thing. Solve for d. The process is exactly the same. So what I have, I'm using the constant multiple rule and as well as the sum rule to break things apart. So d will be the one that is going to balance everything. Will be a ratio of two integrals. One is a b. What is it? 1/2 fx squared dx. And that is the moment with respect to the origin. And the denominator, however, is exactly the same. It is the total mass, fx dx. Okay, so that is my center of mass. Well, center of mass, what I'm talking about, center of mass, it is the y-coordinate. The y-coordinate of the center of mass of that object. The first one was the x-coordinate. So once again, the moment is here, and mass there in the denominator. So it's always the idea is the same. It's a total moment relative to that particular this one is moment relative to the x-axis, and divided by the mass. Okay, and that gives you the whole thing. So let's apply this formula to half circle and see and reproduce the result with this time with absolute accuracy. So the half circle is f of x, once again, is equal to square root of 1 minus x squared, x between 0 and 1. So that is the function that represents upper edge of our half circle. Okay, so I need to integrate the numerator, but fortunately, look at it, how easy it is to solve. And the last one, we don't, not that like the last one, rather the denominator is the same. We're seeing it like for the fifth time. Unfortunately, we don't have to compute it. It will be simply half the area of half circle, which is pi over 2. Okay, so But the numerator is easy. So denominator, integral between -1 and 1, so that's the mass, 1 minus x squared dx, and the answer is pi over 2, half the circle. Okay, so done by trig substitution. So not going to do it again. But the numerator, that is the moment. We will, but fortunately, because of the square, things, I'm sorry, this is between -1 and 1, -1 and 1. But the denominator, so that's the denominator. The numerator is easy because of the square. So it will be 1 minus x squared. So look at it. That one is really simple. So that f of x is squared over there, so the square disappears, and we're facing an integral. It's very, very, very easy. Okay, so let's compute it. Okay, so sum rule. So it's going to be x minus x cubed over 3 from -1 to 1. I believe. Yeah. Right? Okay, so the answer is then, what is it? 1 minus 1/3, so 2/3, 4/3. 4/3, and that is the integral in the numerator, and so the answer is, the d is, according to our equation, is 1/2 of the moment. Look at it, half of the moment. Well, it is the moment. 1/2 of that integral is the moment. So so let's technically it is moment is equal to 1/2 of this. Okay, and so 1/2 of that. So the answer is 2/3. If you want to be careful here. So the answer is 2/3, and then 2/3 in the numerator, and then what is in the denominator? Pi over 2. So the answer is 4 over 3 pi. Is it? Okay, 4 over 3 pi, right? So let's see, is it in anything that what we got? So 4 is, where's the calculator? So 4 divided by 3 and divided by 314. Okay, so 0.42, is that what we got? Yeah, 4.2. Okay, so I mean we can carry out the whole thing one more time if we just if we want to do it over 0, but I think we are pretty good. So approximately 0.428 or something like that. So then once again, this is one axis, and this is the other axis, slightly below half. Okay, and then which produces the center of mass of this object. Okay. So I don't think there is in the upcoming homework. I don't think there is anything from here from this section, so it will appear in the next one. In the meantime, you may be noticing already. I hope you are, that we how restricted we start to feel about the one-dimensional life that we are used to so much in calculus 1. So even computing the area of a circle was a bit of a challenge, because we actually needed more stuff in order to handle it. So one edge and then the other edge, 2 functions rather than 1. Okay, so right now we also did volumes, remember, so that a solid is located in 3-dimensional space, so that already we also need some more room for solving those problems. So once again, if we any kind of throw in any kind of object, the center of mass is also a 3-dimensional, so that's in exactly similar fashion you can find moments of 3-dimensional objects. But the main thing actually is something else. It is motion. Motion in 1-dimensional space is just so boring. So it's like this. This is motion in calculus 1, like this. This is motion. It goes up and down, one dimension. So t is one variable, and this is x is the time, one variable. The output variable is the height, how far you go. It goes up and it doesn't go anywhere. Okay, so that's the best motion we can handle using calculus 1. Okay, so why? Because we have only one variable to spare. There's time and one spatial variable. Okay, so which means that we can go only vertically or we can go horizontally, but we're not simultaneously. So if you want to do this, okay, then you need another dimension. And if you want to go three-dimensional, which happens, like, say if you hit a ball with a spin, that it might create a curve might be like this, might be complex. So you need three-dimensional study as well. So that's why we need high dimensions, and we're moving on from the plane to the three-dimensional space. Okay, so let's just review that certain things that we're going to need, things that we're going to need are exactly the same as before in dimension 2 and on the plane, and those things are the Cartesian system and the ability to measure distances. That's almost all we care about, or maybe there might be a couple of things beyond that, but for the most part, that's what we care about. So, three-dimensional space. The challenge is for the most part, it's getting harder and harder to visualize things and harder to draw for one. So this is the dimensional space, and one day we're going to have a pen. I'm still hoping it for you. I just take a pen and start drawing in space like this, maybe one day. Well, so far I can do it on here, but it is two-dimensional. So that's the problem. That whatever my output is two-dimensional. I'm drawing a plane, even though we're living in three-dimensional space, but we are unable to at this time to draw or write anything in three dimensions. At best, you can hope that maybe there is some. I think I've seen something actually. It's just not coming yet, but like hologram. So holographic drawing at some point we should be able to do it. But otherwise, for the time being, we actually need the Cartesian system even just to visualize things. So many pictures, three-dimensional pictures, start this way. You plot the three coordinate axes, and then relative to those three axes, you might be able to show how things are behaving, where they are located. But it's getting harder and harder. So even if where is the point with coordinates 1, 1, 1? Well, I could do it, but there is a challenge. So I have to move one unit along the x-axis, one unit along the y-axis, one unit along the z-axis, and then where is that point is. These are like 1, 1, and 1 are the dimensions of a box, kind of, and my point is located where. So if I put this box over here, where is my point 1, 1, 1? On the opposite end, on the diagonal from the origin. So if the origin is over here, where all the three axes meet, then this point gives me the 1, 1, 1. So its visualization, as you can see, becomes complicated. But it is easier if you start with lower dimensions and just think by analogy. So it looks complicated, but if you think about it, how do you do point 1, 1? And it is similar. You do one unit along the x-axis, one unit above the x-axis, and instead of building a box, you build a square. Okay, so then your origin was, and it's still diagonal from the origin. So this is the point 1, 1. Okay, so things repeat themselves, and the transition is actually is what we probably should concentrate on. Transition from dimension 2 to dimension 3. Why is it so important or because then you can learn, if you can learn how to transition from dimension 2 to dimension 3, then what do? You can go on. Okay, so you can transition from 3 to 4 and beyond. Okay, so and that's why is it important, because ultimately, well, physics is physics, but it only most of the time, at least at its most elementary, is limited to 3 dimensions. But anything man-made might have any dimension you can imagine. So once again, think about the example that I keep bringing up. If you have 100 commodities being traded, then every moment of time, though there are 100 numbers, and they change possibly in an independent fashion, and which means that you are living in 100-dimensional space. Okay, so then just concentrating on dimension 2 and 3 is not enough if you're studying anything, like I said, man-made. Okay, so data, more specifically. Okay, so let's see how we do that. In fact, there was even one more step, and at some point we started with dimension 1. And so once again, the story wasn't really that different. So once again, we introduced a Cartesian system to a single to a line. Okay, so introduce Cartesian system to a line, then to a plane, then to the space. Okay, but it is done in a manner that is similar. Okay, so think about what I just said. Is that line? There is a line with nothing on it, or there is a piece of paper with nothing on it, or there's space which I cannot even visualize, but this is all around you, and then by mental act we add Cartesian system to it. Okay, so a blank piece of paper, a blank line, and then we start we assign numbers to locations. Okay, so the easiest one certainly was in dimension 1. You can think as if you have a road, and then with and then you introduce like milestones. Okay, so you indicate where your 0 is, the origin of your road, where it starts and goes one way or the other. So that's number 1. Number 1, you have to do the origin. Number 2 is actually the direction of the positive direction. You have to say which direction is positive. And third is the unit distance, or the unit of distance. And then with those 3, you put markings all over the place wherever necessary. 1 mile at a time, then half mile, and more, and then the point is, of course, then you don't have to actually think about locations, points, but you think about numbers. And then with numbers you can do algebra. Okay, so that's the idea of analytic geometry, adding Cartesian system to your that pristine line over there. And then you take the same ideas, and you have this pristine blank piece of paper, and you add to it a Cartesian system. So only since it's a plane like a field, you need 2 axes. The 2 axes. But the ideas are still the same, so in addition to axes, the origin, the units, they could be different as a matter of fact, and different meaning, different, one for x and the other for y. Well, the directions, so the origin, the green one, number 1. Number 2 are the directions, so this is number 2, directions of y and x-axis, and then the units, so that's number 3 here. Which way you're going to go. And then once again, every location on the plane can be expressed in terms of these numbers. Okay, but the difference, of course, that once if it's on the line, all you need to know is the distance from the origin. Period. Okay, so it's 1 number, and here you have 2 numbers, and that makes the whole difference. In 3 dimensions, you can guess that. You will have 3 numbers to identify every location. Incidentally, even in physical settings, you can you're talking about something physical, but actually the dimensions right away go beyond 3. Imagine we're studying motion of an object that is not a point. then its location is 3 numbers. But what else is there? Its location, relative location with respect to space. So it might be rotating around its center of mass, and the angles of the object relative to that center of mass will be 2 more numbers at least, or maybe 3. So, and then what it means is that you're already in 5-dimensional space. So to describe, well, an example you may have heard is airplane. The airplane is, so once again, the location of its center of mass relative to the Earth. Okay, 3 numbers, and then remember those. Anybody remembers those terms? This one and that one. The roll. This is the roll, I think. The roll. The pitch is this, right? And the third one is yawn. I think it is. What is it? Well.
Is it yaw?
Yaw, right? Not yawn. Yaw, right? Okay, so roll, pitch. Is this pitch? Angle of attack. I think this is the one. Possibly. So I can't remember. So anyway, we'll stick to 3 dimensions. Just remember that last arrow over there also has a meaning, because you cannot really stop it with dimension 3 and be happy with it. So that's why you have to look at the whole thing, the sequence of dimensions, and growing into infinity pretty much. So I may have a couple pictures here I want to show you. So okay, so that's dimension 3. Dimension 2, a plane. We start with 2 x-axes. So that's dimension 1. We know how to handle axes. And then once we move to the plane, we take those 2 axes, make 2 copies of pretty much the same axis, but instead of putting them side by side, we put them under 90 degrees. Okay? So and then from those 2 axes, we'll be able to derive our locations on the plane. How? Well, you can see how you go with the. So if you have a location, well, you just find its coordinate in that manner. Okay. So go vertically until you cross the x-axis. That will give you the x-coordinate, or go horizontally until you cross the y-axis. That will give you the y-axis. So that you discover that this point is 2, 3. Okay. And vice versa. You're given any 2 numbers, you can find its location. So for example, if I start with, say, -3, 5, okay, I can find its location. How? Going backwards. So I find -3 over here. Where's my -3? 1, 2, 3. This is -3. That's the x-coordinate. So my point is here somewhere. On the other hand, the y-coordinate is 5. So this is 5. So my point has to lie here somewhere. So all you have to do then is to find the intersection of those 2 lines, and that is your point. Okay, so if P is a -3, 5, that is my point. Okay, so that's Cartesian system on the plane that we're familiar with. And then just take it one step further, we look at what it does to happen in dimension 3. In dimension 3, as you can see, a similar thing happens. We have 3 x's, but since we have of the same type, since we have more room, we assign all 3 x's can be perpendicular to each other pairwise. We create the Cartesian system, and then once again we can use we can create a Cartesian system, as we did, with x's to begin with. But on the other hand, we already have we know how to handle planes, right, in 2 dimensions. So that's why with 3 x's available, you'll have 3 pairs of axes, and each pair creates a plane, and that's what you see on the right. So xy plane. So this is xy plane, and this is yz plane, the vertical one, and this is xz plane. Okay, so that's another way to orient yourself within the space, is not only relative to the axes, which is fine, that's how we do coordinates, but also relative to the coordinate planes. Coordinate axis on the left, coordinate planes on the right. Okay, and so now what about coordinates? How do coordinates work? It is uncomplicated. You can probably guess, but I have my picture just to speed it up. This is how. Okay, so I have a point hanging in the air, and I'm supposed to find its coordinate. How? I go. Well, you can see these pictures over here. So I'm going. What happened here? Yeah, I go from my red point P. I'm going towards the x-axis to find the x-coordinate. So you can see I go vertically, or horizontally. Doesn't really matter. So, but I'm finding one of the planes. So either I go like this, or I go like that. Either way, I discover a line within the axis, and then I take that line. Say it's within xy plane. So this one is the xy plane, and within the xy plane, I find the x-coordinate. Okay. Or alternatively, I go to xz plane, and then I find the x-coordinate of that point. Doesn't matter. Either this point or that point will give me the third coordinate. But ultimately, we do it 3 times, but really it is about building a box. Okay, you can see that box in the very beginning, right here. So to find a box so that our point in question would be lying diagonally from the origin. So that's my point. And this is the diagonal from the origin to my point is what we're talking about. So then the coordinates of the point are the dimensions of the box, x, y, z, 3 dimensions, and you have your coordinates. The only tricky part is that just the same as dimension 2 is that those numbers might be negative. Okay, so box is a good metaphor, but it's a bit of a challenge to think about what the box looks like when its dimensions are negative. So if you can imagine that, then you're good. But generally, that what happens. You could try to jump straight from over here to over there to find the y coordinate. After all, what happens here is I take a plane like this. Okay, so I have my point and I'm looking for the y coordinates. How? I build a plane through my point that is parallel to xz plane. So once again, y coordinate over here. How do I find it? I draw a plane parallel to parallel to the plane that is coordinate plane with respect to the other 2 variables. So y coordinate, plot xz plane. Not xz plane, but a plane parallel to xz plane. And that's what I did. And then if I do, then that's how I discover that point over here on the y-axis that gives me the y coordinate. Okay, so that's how I execute it. And then similarly, I do it for the z-axis. So that's the plane I'm talking about. Is this? This is the plane I'm talking about that you need to find in order to find the z coordinate, which is over here, the location on z. And ultimately, the 3 coordinates are visible to 2, 4, and 1. 2, 4, and 1. So 2 is how far you go along the x-axis. 4 is how far you go along the y-axis, and z vertically how far you go along the z-axis. Okay, so we'll continue a little bit more of that until we move on. Okay, so I'll see you next week.